All right, another example. Starting from rest, Doug uses a horizontal force. So let me kind of draw this. Oh, that's a terribly steep 20-degree angle. So we have a box. The mass is 3.1. We're pushing this crate with a horizontal force of 30 newtons to push the crate up a 2.1 meter high. So this incline is 2.1 meters tall. The angle's 20 degrees. Frictionless slope, just to make it on the easier side, I suppose. We want to know the speed of the crate at the top. So starting from rest, we know V initial is 0. We're asked to find V final. Okay, using these concepts, the net work done on this crate will equal its change in kinetic energy, which I'm going to go ahead and plug in the 1/2 mv squared for kinetic energy, because we know V initial is 0, meaning no initial kinetic energy. V final is what we're looking for. So just jumping to that step. Now, as that box is moving, or crate, I should say, so the force, this pushing force, is horizontal. The normal force is perpendicular to the incline. And the force of gravity is straight down. So when we say net work, we mean the work done by every single force acting on the object as it moves between the initial and final position. So there's no friction. Problem tells us it is a frictionless slope. So the three forces, the normal force will not be doing any work, simply because it is always perpendicular to the displacement. So the displacement is going to be along the slope. Now, we know the force, pushing force, since they say it's 30 newtons, I'm going ahead and assuming that that is constant the whole time. Force of gravity is constant. The work done by a constant force is the force dotted with the displacement. But knowing that it's the components that are parallel to each other, I can say that it is the x component of the force times the x motion, the horizontal motion, plus the y component of the force times the y motion, and theoretically z as well, but we don't have any z directions going on here. When we talk about the work done by the pushing force, I'm just going to come up here to the middle. The pushing force is horizontal. It's in the x direction. So I only care about the delta x when I'm calculating the work done by that pushing force. For gravity, the work done by gravity, well, mg is downwards. All I care about in terms of gravity is the delta y. Because gravity is opposite that vertical motion, I will have the force of gravity doing negative work. Now, by the way, conceptually, just coming at parallel components, this is how I ended up approaching it, because that's my brain thinks conceptually that way. But in both cases, we can always write the dot product as the magnitude of the two vectors. So the magnitude of the pushing force times the magnitude of delta S times the cosine of the angle between them, which we would need this angle in here. For gravity, we could totally do the force of gravity times delta S, and then the angle we would want for gravity would be 90 plus this theta. So this would be the theta for gravity. That works out the same way. So whichever way makes most sense in your head, go with it. All right, so I'm going to go ahead and for my net work, my pushing force F, delta X means the horizontal displacement. Work done by gravity is negative because its force of gravity is opposite that upward motion, so it is going to be removing energy. And this will equal the final kinetic energy. So let's see here. Our force is 30 newtons. We need to figure out delta X. So horizontally, how far does this crate move? We know vertically it moves 2.1 meters because the problem tells us it's a 2.1 meter high slope. So 2.1 meter tall slope. In terms of dimensions, I know the angle is 20 degrees. So sine, cosine, tangent totally apply in this right triangle. I can say that the tangent of 20 degrees is the opposite side over the adjacent side. The adjacent side is what I want. So delta X, that horizontal distance, will be 2.1 divided by the tangent of 20. So 5.7, let's go out a couple digits, 697. So that is the horizontal distance. Traveled. The mass of this crate is 3.1 kilograms, G is 9.8, delta Y was given, that 2.1 meters. So V final is our only unknown. So solving for V final, I have 2 sig figs, so 8.4 meters per second. That'd be pretty fast. So we won't worry about the logistics of him actually trying to walk up a frictionless slope that quickly or at all. Now, side note, if you want to use this F delta S cosine theta, which is fine, the force, pushing force, would be the 30. The delta S we would need to figure out. We know the angle between them is 20 degrees because this force is horizontal. Delta S is up the slope. So we would need to figure out delta S to plug that in. And then if we did minus mg, well actually plus mg delta S, cosine of 90 plus theta. right? Because that's the angle between the force and the displacement. This is what the net work would equal. So we would need to figure out delta S, meaning the length of the incline, which we totally can if we know the height of the incline and the angle, and we want the hypotenuse. We can say that the sine of 20 is the opposite side over the hypotenuse. So we could find delta S that way. And this is the value we would need to be putting in both terms. And this theta is, this is still 20. So 90 plus 20. The cosine of an angle bigger than 90 is a negative number. And so that negative sign would come because of that cosine term. So whichever way is making most sense, going ahead and using the dot product as the magnitude of the force times the magnitude of the displacement times the cosine. But keep in mind, this angle must be the angle between whichever force you're talking about and the displacement vector. So those two vectors. So just be careful, because it's not necessarily the angle given in the problem.